Okay, in this video I'm going to talk about the altitudes of a triangle and the fact that they are bisectors in the orthic triangle. So basically we have, so let's say that we have an arbitrary triangle and we consider the altitudes of this triangle. They of course intersect in this in a single point, and we consider the feet of these altitudes, and so the triangle with the vertices in this feet of the altitudes is called orthic triangle. So this is the orthic triangle, and basically the theorem is that the altitudes in the original triangle are the bisectors in this orthic triangle. So basically this angle. So let me show you on a larger scale. So this angle is equal to this angle. This angle is equal to this angle, and this angle is equal to this angle. So these altitudes, they are bisectors in this orthic triangle. So let's write this as a theorem. So let's denote the points. And the theorem basically says that the lines HA, HB, B, and HCC are bisectors in the triangle HA, HB, and HC. So let's prove this. So it is enough to prove just for one of these bisectors and one of these lines, and the other would follow by symmetry. So basically let's consider, let's draw another picture. So let's consider the and by the way, so this triangle HA and HBHC, like it is called the orthic triangle. Orthic triangle of the original triangle ABC. So let's consider now the ABC, this is HB, and the two other altitudes, and we will prove that BHB. So we will prove that basically these two angles are equal. So that HBB is the bisector of the angle HA, HB, HC. So I will remove it for now because we don't know this yet. We need to prove it. Okay. So notice that the quadrilateral. So let's denote also the orthocenter, the point of intersection of all the altitudes, as h. This point is h. So the quadrilateral. Notice that the quadrilateral A, H, C, H, HB is cyclic. HB is cyclic. Cyclic, it means that all of its vertices lie on a single circle. So like it's inscribed in a circle basically. So there is a circle that passes through all the vertices of this quadrilateral. And the one of the criterion of a cyclic quadrilateral is that the opposite angles. So basically there are several criterion. So one of the criterion is that the sum of the opposite angles is 180 degrees. So if this is alpha, this is beta, then alpha plus beta is 180 degrees, if and only if the quadrilateral is cyclic. And another criterion is that if these two angles are equal, so the angles between the sides and the diagonals that kind of subtend the same side of the quadrilateral. So if these two angles are equal, if and only if the quadrilateral is cyclic. So we will use both of these criterion in this theorem. So first we notice that this quadrilateral HCHHB, so this quadrilateral is cyclic. So let me show you on the picture. It's this quadrilateral, right? This quadrilateral is cyclic because two of its opposite angles are 90 degrees, like the right angles. So H, because the angle AHCH plus the opposite angle AHB, H is 90 degrees plus 90 degrees is equal to 180 degrees, therefore it is cyclic. So from this it follows that it is cyclic. So similarly, yeah. So from this, let's okay. Let's write this more carefully. Okay, so this sum is 180 degrees. From this it follows that AHCHHB is cyclic, and from this it follows so that there exists a circle that passes through these four vertices, and also this circle is the circle has AH as a diameter, because like these two angles are right angles. Right angles in a circle are subtended diameter. So, but basically from this it follows that these two angles are equal to each other. Right, so because they subtend the same arc HCH in this quadrilateral. And also this is one of the criterion of a cyclic quadrilateral. as indicated above. So the angle HCAH is equal to the angle HCHBH, right? So similarly we do with the quadrilateral HAHBC. So it would be cyclic with this circumcircle. So the angle CHAH plus the angle CHB H is equal to, again, 90 degrees plus 90 degrees is equal to 180 degrees. So in this quadrilateral I have two opposite angles that are 90 degrees, therefore it's cyclic. Therefore CHA HB is cyclic. Therefore the angles, so the angle, this one, is equal to this one. I denoted by different, not denote, but like I show it with a different angle mark here, because we don't yet know that it is equal to the previous angle that we considered. So cyclic, therefore the angle HACH is equal to the angle HAHBH, right? Because they subtend the same arc HHA in this circumcircle of this quadrilateral. So but now we consider, so now let's draw another picture. So basically we are interested in this angle and this angle. So this is the, so A, B, C, H, B, H, A, H, C, H. So so this angle and this angle. So these two angles that I showed on the picture, they're also, we'll prove that they're equal to each other, and this would follow from the fact that the quadrilateral AHCHA is cyclic. This is simply, we considered, like if we draw a circle with the diameter AC, then both HC and HA would lie on this circle because it's a right angle, right? So, but it's also a criterion of the cyclic quadrilateral. So because, okay, let's write this formula. So because the angles AHC HCC is equal to 90 degrees and is equal to the angle CHAA. It follows from this. That the quadrilateral AHC HAC is cyclic, and from this it follows that these two angles are actually equal to each other, this angle and this angle, because they subtend the same arc HCHA. So the angle HCA HA is equal to the angle HHA CHC. So in this we simply notice that so this angle is the same as this angle, so it's equal to HCAH. We simply replace the point HA with H, it's the same, HCAH. This angle, which we proved that it is equal to this, right? So, and this is equal to the angle HC HBH, and this angle is the same as, so HACHC is the same as HACH. HACH, and this we proved from this equality, right? So that it is equal to the angle HA HBH. So we look at this chain of equalities, right? So this angle, is equal to this angle. So HCHBH is equal to HAHBH. This is exactly what we needed to prove. This means that HBH is a bisector in this orthic triangle. So from this it follows, so because these are equal to each other, from this it follows that HBH is bisector, or is a bisector, I guess, is a, or is the bisector, is, because there is only one bisector, right, in each angle, is the bisector of the angle HC HB HA. Similarly, we proved that the other altitudes are also bisectors of the corresponding angles of the orthic triangle, and this concludes the proof.